I'm going to do one more of each type of proof by induction, and I'm going to start with a divisibility one. So prove n squared plus 15n plus 4 is an even number. So that's just another way of saying is divisible by 2. So I'm going to write this shorthand again. Is divisible by 2 for all n an element of natural numbers. Step 1, because it's proof by induction, I have to go through my steps. I'm going to prove true. So prove the proposition true for n equal to 1, which is the lowest one that I have in this stage. 1 squared plus 15 times 1 plus 4 gives me 20, I think. That is divisible by 2. It is an even number. So true for n equal to 1. Step 2. Assume proposition is true. For n equal to k. That means anywhere I had an n, I need to put in a k, and I'm going to assume that it is divisible by 2. So k squared plus 15k plus 4 is divisible by 2. Another way of saying that is equal to 2 times something. I'm going to say just any number. If you want to, you could mess around with this a little bit. K squared is equal to 2a minus 15k minus 4. There's an option. You could say 15k is equal to 2a minus k squared minus 4. You could say k squared plus 15k is equal to 2a minus 4. I've loads of options there. All I'm doing is messing around. I'll probably use that one maybe at some stage if I can find a k squared. I'm not saying I'll definitely will, but that's a plan. Step 3. Prove true. For n equal to k plus 1. Okay, so what am I trying to prove? I'm trying to prove that anywhere I had an n, I need to put in a k plus 1. So I'm trying to prove that k plus 1 squared plus 15 times k plus 1 plus 4. I'm trying to prove that is divisible by 2. And let's just go with our proof. I'm going to multiply this by itself, take it to the side, clean it up. K squared plus 2k plus 1 plus 15k plus 15 plus a 4. Clean that up again. K squared plus 17k plus 5. I have no idea if that's divisible by 2. I'm going to go back and use my assumption. Anywhere I see a k squared, I'm going to replace it with this 2a minus 15k minus 4 plus 17k plus 5 is the rest of that. And sorry, so k squared is, have I filled that in right? 2a, there's my k squared, yep. So I end up with 2a plus 2k sorry now, I'm missing something. So k squared plus 17k plus 5 plus 5 plus 20 is what that is there. Sorry, so I never added up all that. So then there's my k squared plus 17k plus 20. 2a plus 2k, and then that's plus 16. Is that divisible by 2? Yeah. So this line is definitely divisible by 2. And this line are exactly the same, therefore this line is divisible by 2. And this line are exactly the same, therefore this one is divisible by 2. And this line are exactly the same, therefore this is divisible by 2. And this line are exactly the same, therefore this is divisible by 2. So this is divisible by 2. I couldn't prove it straight away, but I manipulated and I used my assumption, and eventually I could. And off you go and you write your last line. So we conclude that the proposition is true for n equal to k plus 1. And then off you go to your step 4. The proposition is true for n equal to 1. If the proposition is true for n equal to k, then I've proven that it's true for n equal to k plus 1. Therefore, by induction, it is true for all n an element of natural numbers. So that's a divisibility one. I'll go for a series one next. And one will do. I guess maybe I'll pick question 4 there. So sum up. Okay, so they want me to prove by induction that this is the same as doing this. Well, what is this? This is saying I start off subbing in r is 1 and I add up all the way when I sub in r is n. So that's 3 times 1 plus 3 times 2 plus 3 times 3 plus 3 times 4 plus 3 times n minus 1 plus 3 times n. And apparently this is a fast way of doing that. So I don't have to add up 3 times 1 plus 3 times 2 plus 3 times 3 plus 3 times 4 plus 3 times 5 plus 3 times 6. I could just go 3 times, I went up as far as 6, all over 2, bracket 6 plus 1, get my answer. I don't have to do 3 times 1 plus 3 times 2 plus 3 times 3 all the way up as far as 3 times 100. I can just go, right, the highest number was 100 when I was subbing in for n, therefore that's 3 times 100 all over 2, bracket 100 plus 1, throw that into the calculator and I have my answer. So I can use the left way if I thought it was faster, or I can use the right way if I thought it was faster. What they're asking is prove that this is true no matter the value that you go up to. So no matter if I went up as far as 6, or if I went up as far as 100 or 1,000. So they want me to prove it, and they want me to prove it by induction. So step 1, is it true for, what do they tell me? All positive integers is what it says here. So all positive integers, so the lowest one, is it true for n equal to 1? So if I only went up as far as the number 1, is that the same as 3 times 1 all over 2, bracket 1 plus 1. Is 3 equal to 3? Yeah, true. So true for n equal to 1. Step 2. So I'm not writing this anymore, every bit of this. I want to prove true. No, assume true for n equal to k. Well, that's a really easy step. Anywhere I had an n, I need to just sub in a k. So over here, 3k all over 2, bracket k plus 1. So this is like the kth term of my sequence, or the nth term of my sequence. Doesn't matter what you call it, the nth or the kth. So if you ever needed to come up with this term here, well, you have, you just look at what type of sequence it is. So this one is, the first term is 3, the second one is 6, the third one is 9, the fourth one is 12. That's a linear sequence. If you wanted to come up with the general term of a linear sequence, you could just use your TN of an arithmetic to come up with this. But every question so far, I have been given it. I'm just saying, if that was the case, then you didn't have that, then it's very easy for you to find, and that's why this would be a good revision of patterns. Sorry, that was just a little side note there. Now, so assume true for n equal to k. Prove true for n equal to k plus 1. So on the left, I'm no longer going up as far as the kth term, I'm going up as far as the k plus 1 term. So this is what I'm trying to prove. Trying to prove that that is the same as, now I didn't go up as far as the kth term this time, I went up as far as k plus 1, so that's 3 times k plus 1 all over 2, bracket k plus 1 plus a 1. Now if you want to clean that up, so I know what I'm looking for in a minute, that would be 3k plus 3 all over 2, bracket k plus 2. And if I get that, well then I know I'm right. So what am I doing? I'm going to go and try and prove it now. So I'll go proof maybe. So what do I have here? Oh look, that's what's here, and I'm assuming that all that is the same as this. So I'm going to replace this with this. And I'm going to work with the left until it looks like the right. Again, what is over on the right here? We have 3k plus 3 over 2 times a k plus 2. So I notice over here I've just kind of, if you multiply all that out, I mean, if you want to, you could write that 3k plus 3, k plus 2 all over top by top, bottom by bottom, 2 times 1 is 2. So that's what I'm looking for. And what I notice is down here I have, you know, a fraction plus a fraction. So I need to get this into one single fraction, multiplying top by top, bottom by bottom. And then I need to clean up again. So that's 3k squared plus 3k all over 2. And that's over the number 1. I need to get a common denominator. That goes into itself once. And that goes in there twice, 2 times 3k plus 3. Clean that up. That's 3k squared. I'm sure there's faster ways to do it than the way that I'm doing it, but I'm just writing it all out for you so you can see. Okay, remember you can keep an eye on what you're looking for. So the 2 at the bottom is looking good. I just need to, I think, factorize the top. So that's 3k squared plus 9k plus 6 all over 2. So factors of 18 that add to give me 9. 3 and 6. Yeah, it's actually already factorized up here for me. This is why I was saying there's actually probably, you can see a faster way to do it already if you were kind of keeping an eye out as you were going along. So I'm actually going to just go back to this line, take my 3k out in common, and I'm left with k plus 1 plus 6 into k plus 1. That's all over 2. And that's equal to 3k plus 6 times k plus 1 all over 2. And is that what I had up here? Close enough. I'm going to take the 3 out in common. K plus 1. I'm having trouble fitting that in there, but you can kind of see, I think. K plus a 1. And is that what I had off up here? It is. All right, 3 times k plus 1 times a k plus 2 all over 2. Done. And the very last one then is an inequality one that I'll do. Maybe question 7. So They want me to prove that, I'll even just do the first one, and if that's not enough, I'll do a couple of them maybe. So they want me to prove that 4n plus 2 is less than n squared, or n is greater than or equal to 5, n is an element of natural numbers, and they want me to prove it by induction. So step 1, prove it's true for n equal to 1. 4 times 1 plus 2, is that less than 1 squared? Now, have I taken that down right? Oh yeah, no, so sorry. 1 is not the one to sub in. The lowest number here, even though I'm supposed to sub in natural numbers, is 5. So is it true for n equal to 5? So that is 22 less than 25, true for n equal to 5. So that's step 1 done. Step 2, assume true for n equal to k. So that is 4k plus 2 less than k squared. So we're assuming that that's true. At some point I will use that in my assumption, or in my proof. 3, I want to prove true for n equal to k plus 1. So that means, what am I trying to prove? So that's 4 times k plus 1 plus a 2 is less than k plus 1 squared. And my proof, is that less than that? I don't know, like maybe it's actually worth clearing that up even. So that's 4k plus 4 plus 2 is 4k plus 6, and that's k squared plus 2k plus 1. So is that less than that? I haven't a clue. So I'm going to go with, maybe I'll call this A and this C. And I'm going to use A. I'm going to try and show that it's greater than something, B, whatever B is. And then I'm going to try and show that B is greater than C. And then by default, A will be greater than C. So A is this. Do I have anything like that? Well, look at this. That's very close. All I did was, does this remain true if I had added 4 to both sides? Yeah, if you add the same number to both sides, the inequality remains true. So I definitely know that this is less than k squared plus 4. All I did was, if I added 4 to both sides, I'd have this. So A is definitely greater than B. Is B, sorry, I keep saying greater than, I think, apologies. Is A less than B? Seems to be, yeah, from what I've done up here. I just added 4 to both sides, so A is less than B. Is B less than C? Not sure. So I'm going to move it around, and I'm going to tell you that when I move it around, I end up with, so the k squareds will subtract and cancel off, and I'm going to bring the 1 over, so I'll end up with a 3 is less than, and on the right I will have a 2k, and I'll divide by 2. K is greater than 1.5, or 3 over 2. So this B is less than C when K is greater than 1.5. Is what we're looking at greater than 1.5? Yes, it is. So A is less than B. I keep wanting to say greater than. B is less than C. Therefore, A is definitely less than C when K is greater than 1.5. And off I go, finish my line out, finish my step 4, and that's that. You can let me know if you want me to do another one. That's no hassle.